Everybody. Today we want to study the Deutsch algorithm. Deutsch algorithm is one of the first quantum algorithms, and it has the purpose of proving the quantum parallelism concept. Okay, we are going to see how. In the Deutsch algorithm we have a function f of x which can take either the value of 0 or 1. So for x and x also can take the value of 0 of 1. So if f of x always for 0 or 1 gives 0 or gives 1, so its output does not change with x, we are going to call it this function, we are going to call it a constant function. If on the other hand for x equal to 0 or 1, which occurs with a probability 50%, f of x will change. It can be 0, 1 or 1, 0. So it will change 0, 1 or 1, 0, and we call in this case a balanced function. And we want to make a single measurement to decide if this function is constant or balanced. For this purpose, we are going to build a quantum circuit, which is simple one. So we are going to have here x, sorry. We are going to have here a Hadamard gate with an input 0, another Hadamard gate with an input 1, and then we are going to enter a certain block, an oracle, with here x, and this is y x or f of x, and then we are going to have another Hadamard here. Then we are going to make our measurement in this step here, nothing. Okay, we found that studying this circuit will be much easier if we can divide it into two parts. We are going to study the lower part first, and then we are going to deduce an equation which we are going to use then for the whole circuit together. So let's start by this lower part. I'm just going to draw it again. Here x, here y, x or f of x. Here we have x, and here we have the h, which works on the 1. And let's see the effect, as I said before, of the lower part. Okay, at this section we call this section section 1, and we call this section section 2. Okay, so what do we have at section 1? We have, of course we know, that when parallel lines are entering a quantum circuit, it means there are in tensor product. So at 1 we have x tensor with h of 1, and of course we know that h of 1 is negative, so this is x tensor with negative, which is x with 1 over square root 2, 0 minus 1, and this gives 1 over square root 2 x 0 minus x 1. Okay, when it comes to 2, we see that we have x here tensor with y x or f of x. Okay, let's write this. So after u, at 2, which is after u, we'll have x with tensor with what? With 0, which is the input here, 0, x or f of x minus x with what we have here is 1 x or f of x over square root 2. All right, okay, So as we said before, that f of x could be either 0 or 1. Let's take the two cases. For f of x equal to 0, for f of x equal to 0, what do we have? We have x 0 XOR 0. 0 XOR 0 is 0 minus x. 1 XOR 0 is 1 over square root 2. For f of x equals to 1, what do we have? We have x 0 XOR 1 is 1 minus x. 1 x1 XOR 1 is 0, of course, over square root 2. Okay, of course it is easy to see that these two are just reversed, so it's only negative sign. So to take this negative sign into account, we are going to say at section 2, what do we have exactly? So it's going to be written in the form of minus 1 to the power f of x, x 0 minus x1 over square root 2. Of course, it's very easy to see that this function has the 2 inside, because for f of x, which is here, equal to 0, we are going to have the function this, and for f of x equal to 1, we are going to have the 1 below. Okay, now we can go back to our circuit. Let's write it again or draw it again. Here we have h, here we had 0, here we have h, and here we have 1. This is just the first circuit. For convenience, I'm going to draw it again. X, Y, X, Y, XOR f of x. Here we're going to have an H, and then the measurement, and here this line simply. Again, we are going to give names. So this is 1, this is 2, and this is 3. Okay, let's go back to 1. What exactly do we have at 1? Of course, we have h of 0, and of course, we all know that h of 0 is nothing but the plus. And here we have h of 1, which is the negative sign. So at 1, what we have is plus tensor with negative. It is simply that the plus tensor with the negative gives plus, which is 0, sorry, which is 0 plus 1 over square root 2 tensor with the negative, which is 0 minus the 1 over square root 2. All right? Okay. At section 2, now we are going to use the formula we got before for after the oracle u. After u, what we are going to have, I've just said before that we have minus 1 to the power f of x, which was before x. I'm going to use the same formula I just deduce 0 minus 1 over square root 2. But here the x is what? It is a positive. On the upper line, it was before x, now it is the positive. Okay, so now we can say we have minus 1 to the power f of x with the positive, which is 0 plus 1 over square root 2 tensor with 0 minus 1 over square root 2. Correct? Okay, we continue, which is equal, here equal. which is equal to minus 1. Now we are going to deal with the 0. We are going to deal with the 0. So x is equal to 0. So f of 0, 0 plus minus 1. What we have after that is 1. So it's going to be f of 1 square root 2 tensor with 0 minus 1 over square root 2. Of course, we have here 1. I'm sorry. Okay. Now we want to take all possible cases. We know that f of 0 could be 1 and f of 1 could be 0. F of 0 could be 0 and f of 1 could be 1. These are two cases which will make a balanced function. Okay, let's take one of them. Suppose we take the first one, because anyhow both cases will yield, as we'll see, the same result by the end. So let's take the case of f of 0 equal to 1 and f of 1 equal to 0 in this expression. So what we'll have minus 1, f of 0, as we said, is equal to 1, 0, plus minus 1, f of 1 is equal to 0, 1 over square root 2 tensor with 0 minus 1 over square root 2. This is equal minus 1 to the power 1. 1 is minus. Minus 1 to the power 0 is plus 1 over square root 2 tensor with 0 minus 1 over square root 2. All right, we can take it, we can write minus 1 as common factor. 0 minus 1 over square root 2 tensor with 0 minus 1 over square root 2. Of course, as we said, we could have taken the other value. It's going to yield just a different, here is going to be plus. But anyhow, this is okay and enough for the time being. So this is the output, or this is what will happen after the oracle if we are going to talk, or if we are going to study a balanced function. Now let's see the other possibilities. The other possibility is f of x equal to 1 or f of x equal to 0, which are other two probabilities for a constant function. So again, we can take both, either of them. It will only differ in the negative sign at the output. So at 2 again, what will happen if we take a constant function? We just go again to this function and substitute with f of 0 equal to, we said we are going to take of 1. Okay, so we are going to take f of 0, sorry, this case. So we are going to take f of x equal to 1 or f of x equal to 0. We'll take the case of f of x equal to 1. Okay, so now at 2, if we substitute for f of x equal to 1, it will give minus 1 to the power 1 of 0 plus minus 1 to the power 1 for 1 over square root 2 tensor product with 0 minus 1 over square root 2, which we can easily write at minus 1, 0 plus 1 at square root 2 tensor product with 0 minus 1 at square root 2 divided by square root 2. Okay, it's better now to write them in a unified way. So at 2, which is, I can call phi 2, of course, no problem, is going to be plus or minus 1. I'm just going to take this and this one. Okay, so it's plus or minus 1, as we said, it's 0 minus 1 over square root 2 tensor with 0 minus 1 over square root 2 in the case of balanced. The plus minus 1 is just for the two different cases, as we said. And for f of plus or minus 1 is going to 1 plus 1 over square root 2 tensor with 0 minus 1 over square root 2 for constant. So we have these two output, or these four output, because it has plus or minus in both cases, but it will not differ because, as we know, we are going to take the probability, which is square of the amplitude, so the negative will disappear. So if we have a balanced function, it's going to be a minus. If it's going to constant, if we have a constant function, it's going to be plus. But let's remember that we are still at 2, at section 2. Yes, we have an h. Okay, let's see what the h is capable of doing. Of course, we know that h, we have here a negative, it will be a 1. Here we have a positive, it will be a 0. So after last h is going to be plus or minus 1. Of course, the 0 will be negative. This is negative, so it will give a 1. Okay, tensor with 0 minus 1 over square root 2 balanced, and it will be plus or minus. This is plus, so it will be a 0 tensor 0 minus 1 over square root 2 if it is constant. So what exactly happened? If we measure the first qubit, remember this is the first qubit, or the qubit in the line above, and this is the qubit in the line, so this is the line above, this is the line below. We see that with probability 100%, we measure a 1 if it is balanced, and with probability 100%, we measure a 0 if it is constant. And all what it required is a single measurement. So a single measurement, and this is exactly what we call quantum parallelism, because we don't need to make several measurements or successive measurements. A single measurement will allow us to know if the function is balanced or constant. And this terminates what we know as the Deutsch algorithm. In the next lecture, we are going to talk about a general form of the Deutsch algorithm, which is the Deutsch. This is next lecture. We are going to talk about the Deutsch-Josa algorithm. It's more general, so it has more steps, but hopefully it will be clear. Thank you for your attention. Hope to see you soon.